Welcome to this next video in the playlist on vector spaces. In this video, what we're going to explore is the concept of a linear combination and the span of a set of vectors. Okay, so what I'm firstly going to do is just do the setup. Okay, so we'll just remind ourselves of what a vector space actually is. We'll draw a little picture. Then we'll start with discussing what a linear combination of a set of vectors actually is, and then what we'll do is discuss what the span of a set of vectors is, and we'll see how the span of a set of vectors is actually a subspace of the vector space. Okay, right, so firstly let's just remind ourselves then of what we're working with, which is a vector space. Okay, so I'll just remind you, a vector space over a field capital F, okay, which will denote V for the vector space, and our field will denote capital F. Okay, so this is an abstract vector space over some abstract field. Okay, right. This fundamentally starts off as just a set of symbols. So I'll draw that first. So we'll have a box representing our set of symbols. Okay, so here is the vector space capital V. Okay, and fundamentally it's just a set of symbols that you've made up. Okay, and these symbols within the vector space, they are called vectors. Okay, then what this vector space set is actually going to have defined on top of it is going to be two composition laws. Okay, now the first composition law is called addition, and this is a composition law of all of the vectors with other vectors. Okay, so you compose one vector with another vector, so we have a great big composition table here for addition. Okay, which I'll colour in orange here, and what you'll do is you'll give every single element of the vector space, every single vector in the vector space, a row in this composition table. Okay, so just drawing one of them in, here is a row corresponding to a vector in the vector space. We'll have little v, a vector in our vector space here, and here is its row corresponding to it. Okay, and then what you'll also do is you'll give every single vector in the vector space a column in the composition table. So you'll put all of the vectors up here as well. Okay, and then what you'll have is this great big table which is every possible addition that you could possibly think up, basically. Okay, so if you want to add one vector to another vector, let's say we want to add v to v bar, so here is another vector in our vector space, v bar. What you do is take the row corresponding to v, so if you were considering v plus v bar, you take the row corresponding to v in this addition table, you take the column corresponding to v bar over here. So here is the column corresponding to v bar. Sorry, the bar isn't particularly visible, so I'll colour it in to make it more obvious. We'll colour code v bar here in purple. So this is the column corresponding to v bar here. Okay, and we'll have a v, I think, in, what colour should we do it in? Green, I think. Okay, so here is v in green here. Okay, and that entry, that intersection of the row and column, this little box in this great big addition composition table, that will contain the answer to what v plus v bar is equal to. Okay, and that answer will be some other vector in the vector space. So you go through every single possible combination of adding one vector in this vector space to another vector in this vector space. They will all have entries in this great big addition composition table, and all of those answers will be other elements of the vector space, and that fundamentally is what tells you how to add two vectors together. Okay, now we know that that addition composition table, in order for this to be a vector space, has to obey some beautiful properties, and those properties are the properties of an abelian group. Okay, so the addition composition table is going to obey the properties of an abelian group. Okay, and I'll just list those off. If you want these in more detail, look at the video on the definition of a vector space. But just listing them off, it needs to be closed under addition, which means that all of the answers in this addition composition table need to be back within the vector space. Okay, it needs to be associative, which means that if you add three things together, it doesn't matter where you put the brackets, there's one and only one answer to that. It needs to have an additive identity, okay, which means that there needs to be some vector vector in the vector space which we call the 0 vector, which will add to any other vector either way round to give that other vector back again. There needs to be additive inverses. That's axiom number 4, which says that for any vector in this vector space there must be another vector, the negative of that vector, which will add to it and give the additive identity of the 0 vector, and it needs to be commutative. Axiom number 5, which says that it doesn't matter which way round you add two vectors together, the answer is the same thing. So v plus v bar should be the same as v bar plus v, which means that this addition composition table must be symmetric down the diagonal line. Okay, so we have to have this very nice addition law defined on top of our set of symbols, which obeys all sorts of axioms, 5 axioms, the axioms of an abelian group. Okay, then what we have is also another composition law on our vector space, which is called scalar multiplication, which is denoted by a times symbol. Okay, and this is not a composition where you compose one vector with another vector. So it's not a composition of two vectors. Instead, it's a composition of an element from the field, capital F, with a vector from the vector space, capital V. Okay, so what this time you'll do is you'll dedicate all of the rows of this scalar multiplication composition table to elements of the field rather than elements of the vector space. So this vector space capital V is over some field. There's some field that's connected with it, and this is where the field actually comes into the definition. Okay, so you have to be able to multiply all of the elements of this vector space by the elements of this field. And remember, the field is an algebraic structure in its own right, so it's a set of symbols with composition laws defined on it. Specifically 2 composition laws, an addition composition law of its own and a multiplication composition law. Okay, but now it's coming into play here. So we'll have all of the elements of our chosen field, capital F, given rows in our scalar multiplication composition table. Okay, we'll also have all of the elements of the vector space then up here given columns. Okay, so you'll have every single possible vector in this set given a column in this scalar multiplication table, and then you'll have all of the elements of the field down here. And then what you can do, what you will define, is what any element of the field, which I'll call C, so C is some element of the field and V is some element of the vector space, you will define what C scalar multiplying V actually is. Okay, and that will be the entry in this composition table where you take the row corresponding to the element C, and I should have drawn these pictures bigger. Okay, I'll colour code it again. So here is C, the element of the field, and then what we'll have is our vector V here, and we'll take the column dedicated to it. So here we'll have this column dedicated to V here, and then the place where the row corresponding to this field element C and the column corresponding to this vector space element V intersect, this box, that will contain the answer as to what C scalar multiplying V actually is going to be equal to, and it will be some other vector in the vector space. Okay, so I can multiply any element of the field by a vector to get another vector in the vector space, and that operation is called scalar multiplication. Okay, so I'll just colour in my scalar multiplication law in purple here, so that we have a great big composition table here telling us, defining what any element of the field scalar multiplied by any element of the vector space is actually going to be equal to. And again, you can't just make this up and expect it to be a vector space. It won't be very interesting. Of course, you can make up these addition and scalar multiplication rules. Okay, you can define your own algebraic structure, but you won't end up with something at all interesting unless it obeys a bunch of beautiful properties. Okay, and to be a vector space it has to obey a bunch of beautiful properties that mean that it's especially interesting to study. Okay, so addition had to obey the abelian group axioms. Scalar multiplication has to obey a bunch of axioms as well, which are categorized into 4 sections. Number 1 is closure, which is the easiest to understand. That, remember, means that all of the answers in here must be elements of the vector space. You can't just put in some arbitrary symbol that isn't within this set, basically. Okay, in addition then, axiom number 2 is associativity of scalar multiplication with the field multiplication. That says if you multiply a vector by elements of the field which we'll call scalars twice, so you multiply it by 2 scalars, then what you can do is you can associate the multiplication of the scalars together and just multiply the two scalars in the field, and then multiply the answer which is an element of the field. You can scalar multiply that with your vector and that will give you the same answer. Okay, axiom number 3 then concerns the identity element of the field, specifically the multiplicative identity of the field, and says that 1, the multiplicative identity of the field, must multiply by any vector to give that vector back again. And then axiom number 4 is the two distributive laws. And as I say, if you want those done in more detail, do watch my video on the definition of a vector space. This is supposed to just be a quick reminder of that. Okay, so there's our setup, there's a reminder of the structure of a vector space. Now let's actually discuss what is meant by a linear combination. Now, in order to discuss what is meant by a linear combination, we need to have a set of vectors that we are talking about, because a linear combination of what? Okay, you need to have a set of vectors which you're talking about linear combinations of. Okay, so what we're going to do is we're going to take a set of vectors which we'll call capital S. Okay, and capital S is going to be a subset of our vector space capital V. So it's going to be a subset of elements from the vector space capital V here. Okay, right. And for our purposes, I will write S out as a finite set of vectors, although the concept does extend to infinite sets of vectors, but for our purposes we will just be talking about finite sets of vectors. Okay, so we will have a set, capital S, which is going to be a finite set of vectors. Okay, and this is going to be a set of vectors, and I'm just going to pick vectors from this vector space. So I'm just going to give them arbitrary names. So we'll have v1, which is our first vector in the set, v2, and we'll go all the way up to vn, where n is some positive integer, some natural number basically. Okay, so here is a set of vectors. Okay, so it's certainly a subset of capital V. It's got a subcollection of the elements of capital V. Okay, so just adding this onto the picture here, we will have v1, v2, v3, and then it'll go all the way on, and we'll have vn. These are all just vectors from the vector space. So I've just picked some symbols out of this great big set, and I've stuck them into a set by themselves, and I've called this set capital S. Okay, so now we are ready to define what is meant by a linear combination of the vectors in this set capital S. So a linear combination is going to be a new vector in the vector space capital V, but it's going to be a vector that is related to these n here. Okay, and the way it's going to be constructed is what you're going to do is you're going to scalar multiply each of these vectors here by some element of the field and then add them together. So this is what is meant by a linear combination. I'll write it out and then we'll discuss it further. So c1 v1 plus c2 v2 plus, then you'll go on c3 v3, c4 v4, all the way up to cn vn. Okay, and this is going to be an element of the vector space capital V, because all of these ci's, all of these are elements of the field where I varies between 1 and n. Okay, so all of these elements here, and I'll colour them all in, all of these things that I've got in front of the vectors, these are just elements of the field capital F. Okay, so what this means is you've come up with some arbitrary elements of the field. Pick whichever ones you like, it does not matter. Then what you've done is scalar multiply the vectors in this set by those elements of the field, basically. Okay, to get new vectors. So all of these things here, c1, v1, that is a vector in the vector space, c2, v2, that is an element of the vector space, all the way up to cn, vn, that is an element of the vector space, because all we're doing is scalar multiplying vectors that are in our set here, capital S, by scalars. Okay, and we know that we'll always get an answer that's back within the vector space, and then what we're saying is add all of these n vectors that we've now got outlined in red here together, and of course when you add lots of vectors together you'll end up with another vector in the vector space, because the first axiom that addition must obey as an abelian group is that it must be closed. Whenever you add two vectors together you must end up with another vector in the vector space. Okay, so that's why I can say that this thing that we've got here is another element of the vector space. Okay, so this is what is meant by a linear combination, so I'll just write that out again down here. Okay, so we would say that this new vector that we have created here, which is an element of my vector space, is a linear combination of the vectors v1, v2, all the way up to vn. Okay, so that is what is meant by a linear combination of the vectors. A vector that you can construct in the vector space by taking some scalar multiple of each one of these n vectors in the set capital S and then adding them all together. Okay, so to explore this concept further, let's now define what is meant by span of the set S. Okay, so what we will write is span of the set capital S. Okay, and what this is going to be defined to be equal to is the set that contains all of the vectors in the vector space which are linear combinations of the vectors in this set capital S. Okay, so writing this explicitly out then, what we want to do is put in absolutely everything of this form, C1 V1 plus C2 V2 plus all the way up to Cn Vn, where the Ci's are elements of the field capital F. So we put in absolutely all of these linear combinations of the vectors in that set capital S into a set, and that set, that subset of the vector space capital V, and I'll just put that in, this is a subset of the vector space capital V, that is going to be what is meant by the span of this set capital S. Okay, right, so let me just spell out exactly what you have to do then to construct this. So firstly, we have picked this set of vectors. So we picked some vectors, v1, v2, all the way up to vn in my vector space. And I think I'll just redraw that picture out down here. Okay, so here is my vector space once again. Okay, and I'll just outline this in turquoise here. So here's my vector space. I've then got these vectors v1, v2, which are just arbitrary elements of this set. They're just symbols from this set, all the way up to vn. And now what I'm doing is constructing loads of other vectors. So what I'm doing is I'm saying, okay, we will let all of these scalars here vary over every element of the field. Okay, so C1 I will let vary over every element of the field. Okay, C2 I will let vary over every element of the field. So for every possibility that I can put in C1, I will go through all of the possibilities in C2. And for all combinations of C1 and C2, I will then let C3 vary over all the elements of the field. And this goes on and on, all the way up to Cn. So I take every possible combination of elements of the field, n elements of the field here. Okay, I work out what every single one of these linear combinations involving that combination of elements of the field is actually going to equal. I take all of those vectors one by one from this vector space and I stick them into this set. Okay, it's a huge amount of work, but that is fundamentally what this means. Okay, so it's a lot of work to actually manually construct one of these things. Okay, right, so to give you a bit more intuition still, let's just think about what this will be if we just have some small sets, okay, because smaller sets are easier to understand. So let's think about what will happen if we take, for instance, the span of a set containing just one vector. So now let's just have a set containing one vector. So this is my set S, and because it's such a small set, I've actually just written it in there as the set. Okay, I suppose I should put brackets around there. So there's my set. Okay, so what would I do here? Well, now I'll just have one vector. So this, by definition, will just be all things of the form C1 times V1, where C1 can vary over all elements of the field. So all I will do in this case is I'll just multiply V1 by every single element of the field. I will take all of the possible scalar multiples of my vector V1. Okay, so to make this even more plain, if we have our scalar multiplication table here, okay, here are all the elements of the vector space up here. Here are all the elements of the field down here, given rows in the scalar multiplication table. What we are effectively doing is we're going to say, okay, look at the column dedicated to this element V1 here. Okay, so here is this element V1 which we've used here, and we're going to go through all of the elements of the field and scalar multiply all of those elements of the field by V1. So we're going to be looking at this entire column basically of entries, because we're going down all the elements of the field. So one by one we'll go down all the elements of the field, we'll scalar multiply V1 by those elements of the field, and we'll take the answer in that entry of the scalar multiplication composition table, and overall this will end up going down all the entries in this column for V1, putting all of those entries into this set. Okay, so effectively we'll just end up with this set of entries in this column basically, and that's what is meant by the span of a set containing a single vector. Okay, so to put this on this picture, it'll just be a nice little subset of my vector space where I've just multiplied V1 by every single element of the field. Now there's one vector that we can absolutely always say that will be in there, okay, and that's the 0 vector. Okay, so the 0 vector will always end up being in here, because one of the linear combinations that you'll end up with is where C1 is going to be equal to the 0 element of the field, the additive identity in the field. Okay, so understand there's two zeros here, the 0 vector in our vector space and 0 in our field, the 0 scalar. Okay, now when you multiply any vector by 0, it gives you the 0 vector. And you can prove that straight away from distributivity, and I believe we do that in the video on definition of a vector space. So in absolutely all of these you'll end up with the 0 vector being in there. Okay, and that will be the element of this column corresponding to multiplying V1 by 0 element in the field, so you end up with the 0 vector here. Okay, so to gain more intuition, let's now go up a step, okay, and this is as far as we'll go, okay. Let's now consider the span of a set containing two vectors, v1 and v2, okay. So what will this mean? This will mean all things of the form c1 v1 plus c2 v2, where these ci's can vary over all elements of the field, capital F. Okay, so let's draw a picture of what we're going to do here. So, we could just let C2 equal 0, okay? C2 can vary over all elements of the field, capital F. Okay, so one of the values it can take on is 0. Okay, now if C2 is equal to 0, then we're still going to have to vary C1 over all elements of the field. But if C2 is 0, then this thing here will just equal the 0 vector, so the answer will just be C1 times V1. So what that instantly tells us is that the span of this set containing two vectors will completely contain the span of V1, okay, and the same argument applied now the other way round will tell us that it also has to contain all of the span of V2, okay, because you can let C1 equal 0, that will make C1 V1 the 0 vector, and then you'll get all of the possibilities for C2 times V2, where C2 can vary over all elements of the field. So what this instantly tells us is that the span of this set containing V1 and V2 has to contain the span of the set containing just V1 and the span of the set containing just V2. Okay, so drawing out another picture here. Okay, we've got these two elements of our vector space, V1 and let's have V2 here. So firstly let's construct the span of V1. So let's say that this here is the span of the set containing just V1. Okay, I'll just highlight that up. So here we go, this is the span of the set just containing V1. So that's V1 scalar multiplied by all elements of the field. Then let's mark on span of V2 here as well. Now the reason I've got them having a non-empty intersection there is because they will have a non-empty intersection, because remember the span of a single vector always contains the 0 vector. So both of these will contain the 0 vector, so at least in their intersection they'll both have the 0 vector. Okay, so here is the span of the set containing V2 here in red. Okay, so that's all V2 scalar multiplied by all elements of the field, and then quite simply what you need to do is you need to add everything in the span of V2 to the span of V1 and take all possible combinations of C1 V1 plus C2 V2. So what this will kind of end up as on my picture is this square here. I go through all of the elements of the span of V2, and for every single one of them I add that to every single element in the span of V1 and see what I end up with, and that will end up giving me all the linear combinations of this set of vectors V1, V2. So overall this will end up as being like this square. So that's kind of the intuitive picture of what the span of two vectors means here. Okay, and you can kind of then extend this to 3 vectors, and it becomes a bit more difficult to visualize with 4 vectors, because when you go into 3 vectors you'll kind of want to visualize having to go into three-dimensional space, having another one going into the page, and then ending up with a cube, but then it breaks when you try and go higher at that visualization. But of course, as far as abstract symbols are concerned, we can go to however many vectors you want. Okay, right, so that then is the definition of what the span of a set of vectors actually is, and that's the kind of intuition about what it actually means. Okay, what we will do now is we'll have a break, okay, and then in the next video what I want to prove is that no matter what set of vectors you take, so no matter what S actually is, when you take the span of a set of vectors, it ends up being a subspace of the vector space. So I've argued that it is a subset of the vector space capital V. What I now want to argue is that the span of a set of vectors, no matter what the set of vectors actually is always going to be a subspace of the vector space capital V. Okay, so that's what we'll do in the next video, and the way we'll tackle this is just by trying to prove that this subset of the vector space actually obeys those three criteria that in the video on subspaces of vector spaces we proved would then mean that the subset with the inherited composition laws from addition and scalar multiplication on it would actually be a vector space in its own right.